So hopefully for the next hour, I'm going to give you a quick blast on algorithmic performance, right? Technically, I'm going to talk about runtime performance rather, but anyways, we'll get the difference later. Why doesn't this thing accept mistakes? All right. So what we talk about today is a basic algorithm, idea of what we're doing here in terms of algorithms in general. And we're going to be talking about something called algorithmic runtime. And to talk about algorithmic runtime, we're going to talk about one way people measure it. You want to say that? I don't want to really measure. It's more about I don't know what that is, right? Here's what we think about this, right? And after we do that, I'm going to look at a couple of examples of algorithms. And obviously their orders. I'll let you tell me what their orders are. And then we look at some other measures. Other common measures, and I'll give you some of them, right? Pretty much it. Hopefully, in and out, see that. Okay, let's do this one. All right, so first question, what's an algorithm? Open flow. I go. Sequence of steps. Any other ideas? Steps taken to solve a problem. Okay, we got that. Let's go with that now, right? Okay, I came up with these 3 points on the typing slide the day before. So we have to have a clear set of instructions for completing task. I want to clear, I mean, there is only one way to read it, right? We can't have 2 interpretations of the same set of steps. The second thing is that algorithms in general, I'll give it slides right after write down my slides. So if you want, I can email it slides. Yeah, I want to focus on what I'm going to talk about. Try to get the idea while we're here, right? So focus on getting the idea. The second thing about algorithms, in general, though not always true, they're written to be language independent. Okay? But you have to write in such a way it's easy to translate it into a language. And then the last one is gives us a way to talk about the solution to a problem. Okay? So then the obvious question is, why would you want to study it? Thoughts? Is it obvious? It's obvious. Okay. It's too obvious, right? Okay. That was very odd thing, right? The idea is to be able to actually write down the steps so that you could put it in the machine, and also because, well, it gives us a way to actually talk. Okay. But most of the time we're spending here is actually talking about algorithms. So here we go. Think of a number, an integer, like whole number, no fractions allowed, right? Between 1 and 100. Right. Okay, I want you to guess and then tell me too low or too high. All right, who shall I pick on? All right. Yeah, because all right, this is number 1, 2, 3, 4. Okay, what is my algorithm? I can increase by 1 each time, right? That's easy. My algorithm was I start from the lowest number and just finish an act, right? So I'm going to call that a simple switch. How many steps does that algorithm I just used take to get that answer? In a worst case, 100. In a worst case, right? Because somebody can say 100, I don't think 100, right? Okay, so it's 100. What on average? I had 50, right? Okay. What if I'm sure it's all you know, mess with me? Every single time she does it, it's 100. Yeah, every single time I run out, she always think of 100 all the time, right? Okay, when people are talking about average, right, they're making some assumptions. Assumption number one, the word average means more than one time, right? So this algorithm, for it to work, means I have to do it multiple times to get an average. Cool. Now I'm saying this, everybody's nodding, and I'm very sure. Well, okay, I'll wait for the eventuality and I'll remind. Okay. Average means we're talking about it doing multiple times, right? That is the first assumption. The second assumption is that the numbers that you're giving me are going to be normally distributed, or sorry, not even normally, equally randomly distributed across 1 to 100. That is not always a valid assumption. Typically, we will make that assumption, but in some cases, you don't want to make that assumption. So, like, say, for example, there are some algorithms and some situations where you might want to assume a normal distribution. There are some you want to assume like Poisson, like comps, for instance. Hold on. Like when you're assuming how data packets are coming in a network, we use Poisson and lots of comps. Right? We use normal because a lot of stuff in life is normal distributed. Right? We might use linear because we want to assume random, like a complete random across the spectrum. So there are a lot of different assumptions you might want to make. But we're going to go assume, if we assume random, this is usually the assumption I'll make, it's going to be 50. Right? Ask different people. Yeah. All right. So let's try this again. Algorithm number 2. Think of a number. Who is the number? Looking at you already, though. All right. Here's the number 50. Too low, 75. How do you mark? 60. Too low, 65. Too low, 70. 71. 73. 72. Wow. Okay, good. So the answer is 70. Right, okay, no problem. Okay, so what was the algorithm using? I know he's a very poorly one. What was the algorithm using? Yeah, what I was trying to do, but I couldn't do math. So basically, I went in the center first, around the 50. You said too low, and I was somewhere in between, right? From 51 to 100. And you center there was 75. And when you center of the remaining range, then keep going each time, right? That's an example of a binary search algorithm, right? So, same question. How many steps does that take in the worst case? Any takers? No takers on that. Everybody, I can see the math happening. The gerbil's running. All right, cool. Yeah, a little evil if you don't know the math, but okay, I'll do it. So let's simplify it out, right? Let's say we were guessing between 1 and 50, right? So the first thing I would try to answer would be 8, right? So 8. And then if it was higher than 8, I'd go to 12. If it was lower, I'd go to 4. If it was higher than 12, I'll go to 14. If it was lower than 12, I'll go to 10. If it was higher than 4, I'll go to 6, 2. Yeah. And we're seeing how we progress, right? So does this diagram help you out with how many questions would have been asked? How many steps would have done? Any worst case from this diagram? 3, 1, 2, 3, 4. I got 4. I got 3. Oh, I guess the last one is not a question again because after our discussion by then. But basically, in 4 steps, I'll have the answer, right? More. Yeah. So this is called a decision tree. Well, in this case, binary, a binary decision, right? Obviously, so there's 2 choices at each point. Oh, sorry, two routes you could take. Obviously, the most we could go is the depths of the tree, right? 1, 2, 3, 4. That's just 4 on the bottom, right? Cool. So, oh yeah, we answered that already. How many moves did I at most I need? The answer is 4. 1, 2, 3, 4. Cool. In 4 moves, I'll have the answer. Where the fourth move is, I'm saying the answer, more or less, right? And in this case, I'm saying the number of levels in this tree. With me so far, right? Okay. Other question: how many nodes are in this tree? The answer is on the top, right? It's a pretty name in the slides. 15. It's 50 numbers, right? It's 50 possibilities, right? So, all right. So here's a little formula here. N, the number of nodes, is equal to 2 to the L minus 1. Where that comes from? Okay, when I had just one node, right? How many levels is that? 1. So that is 2 to the 1 minus 1. And then I have 2 to the 2 minus 1, 4 minus 1, right? In a binary tree like this, one thing I want you to recognize is that we always add in a power of 2 each time, right? So 1 thing, that's 2 to the 0, and then you add two things, that's 2 to the 1, and you add 4 things, that's 2 to the 2. Each level of the tree always adds a binary number, a power of 2. Makes sense, right? Which means you're always 1 less from a power of 2. That's a funny piece of math, but yes, that is that. Anyways, so can you make L the subject of this formula? Well, first you rearrange it. So you put the 1 over by the n, yeah, and you take logs on both sides. So we're taking log base to both sides. I would put L to the front because you could do that with logs. The power comes to the front, and you have a multiply, and then I simplify, right? So that means if you had to get L from that tree, you just take log base 2 of the total number of decisions you have to make, right? So what that formula is telling me is that if I have 15 numbers which to choose from, right? If I use a binary search, I can get it in log base 2 of 15. No, sorry, 16 steps. Make sense? And that's how you get the height of a tree. All right. So on average, how many steps would I take, right? So we answer the worst case scenario there. So on average, how much do you expect I would take? How many steps? You're too silent. I suppose you're always supposed to know this answer, but okay. In the worst case, we take in log 2 of the number of nodes, right? Which is in this case 4. But on average, how many times would I have had to ask the question? Assuming that we could have a random number each time in the 1 to 15 range. Okay, how about this? Don't try to give me a number. Try to reason it out based on how the diagram looks. Which level in the tree has the most numbers? Level 1, level 2, level 3, or level 4? Level 4. So if I had to do a probabilities game, right, we have to just do probabilities here. I want you to recognize something. What percentage of numbers are in level 4? 8, 8 out of 15. So that's more than half. So that means more than half the time they're going to reach level 4. If I have a random distributed things, right? More than half the time they're going to reach 4. In the off chance, 1 out of 16 are going to just hit the mark with 8. So from just probability alone, a probability would be on average closer to the bottom. On average. Make sense? Yeah. So I would estimate 3 to 4, right? If I didn't have a formula, I'd kind of like, 3 to 4-ish. Yeah. Okay. So, okay, what are that? Let's do it a little differently now. We did a 1 to 15 case, or what a 1 to 10. How did decision tree would look for 1 to 10? What would be my first response? What would my first guess? Okay. Yeah, we go somewhere in center, right? So I go with 5, please. Then if it was higher, then I go with 8. If it was lower, I go with 3. Well, let's see. Seems like I did that a lot of my bad, whatever. Anyways, here's the tree for 1 to 10. What does the tree look like differently now? The bottom of the tree not as full, right? The last leg didn't get full. Yeah. Oh, there was another number. All right. Okay. So in this thing, how many moves at most did I need for 1 to 10? 4 again, right? Because again, the depth of the tree didn't change, right? Because think about it in terms of powers of 2. 1 is power of 2. That's equal 1, 2, 4, 8, 16. So between 8 and 16. Yeah? 2 to 4 is 16, 2 to 3 is 8. So because I'm between those two, then obviously my lowest branch is going to be 4. Because I have to have something in fourth level, all the way down. And I'm very cool with that, right? So did the formula work out? If you apply the same formula we learned from before. L is equal to log base 2 of n plus 1. So 10 plus 1 is 11, log base 2 of 11. We know that's somewhere between 3 and 4. Yeah, so the formula works just fine. Right? All right. So now we do a little bit of a harder thing. What about on average? Average looks a little bit, I kind of look at it and be like, the last level is now not as filled. Yeah. So the way they actually do this in these kind of competitions is they actually do a frequency distribution with some probability. So if I just have to add it up, in level 1 I have 1 node, level 2 I have 2 nodes, level 3 I have 4, level 4 I have 3 nodes. Yeah. So then on average I would go to 1 by 1 level 1, 2 level 2, 3 level 4s, 4 level 3s and 3 level 4s. Yeah. And on average I would work that out to be somewhere around 2.7. Yeah. So between your 2 and your 3, because 3 is the most full anyways. So again, we kind of veering towards the bottom. Not all the way bottom, because the bottom is not fully full, but the next best bottom, right? On average. Yeah. So I want you to think about this in terms of if the tree gets a really huge now, right? We have millions in the tree, millions of numbers. Right? And because we don't want it to guess between 1 and 15, we could do that, right? We have millions, then the tree gets a little bit longer. In those kinds of cases, people will start to approximate and say, well, the worst case is obviously the bottom of the tree. Makes sense. But the average not so far from the bottom anyway, so yeah, that's what the bottom, right? So in practice, the approximate, the average case for binary trees the same as the worst case. Okay? And in practice, they would just say, well, log base 2n. And you would see Anil and Akash just say, well, see log base 2n. Right? This is why they say. I don't think they explain this. Okay? So going back to our original 1 to 100. In the worst case, what do you expect 100 to be? Okay, 2 to the 4 was 16, 2 to the 5 is 32, 2 to the 6 is 64, 2 to the 7 is 128. So I would expect it between 6 and 7. Yeah, log base 2 of 100 will, sorry, 101 will be between 6 and 7, which means that the 6th level will be full, and the 7th level will have some stuff. Not fully full, because not reaching all the way to 128. Yeah? So I'd expect it'll take about 7 steps to get to 100, to deal with 100. So is that better than your sequential search? Because worst case for the sequential search is 100. For binary search is 7. Way better. And on average, around the same thing. Yeah. In practice, it'll be a little bit less. It's okay. Again, we can average it about the about 6. Yeah. Because again, in practice, they will say that the worst case and average case are about the same. Okay. Which is an approximation they use in practice. All right. Hard question. Is there a difference in a best case for either one of these? What's your best case scenario? One step. First number guess. Yeah. Price is right? I got the answer. So I want you to take a look at this. Let's take about binary search, which is on the left, and simple search on the right. If we had a dictionary, and I'm looking up a word in dictionary, and I had 240,000 words in each. Binary search, in the worst case, will take 18 steps for 240,000 things. Simple search will take 240,000. See the large discrepancy, right? And the average case is a huge disparity to talk about here. So, okay, let's talk about Facebook then. In Q2 of 2020, there were 2.7 billion active. I read them checks, right? Active users on Facebook. So if you had to search for your friend on Facebook and you're typing it in, right, you give me an answer. It would take a computer 32 steps if it could binary search to find the person you want, right? Whereas if it was using simple search, 2.7 billion, which might take some time. Make sense? If we assume, I made some assumptions about the machine there, that it could do 20,000 instructions per second, that's CPI of 4. It would take about 2.5 milliseconds for simple search, whereas about 2.5 days to search all these on Facebook linearly. Hope you get the idea, right? So you call binary search an example of log time, whereas simple search is linear time, right? Log time algorithms are obviously basically faster in general. And I come to this conclusion without making any assumptions about the machine. I just did that just so that you could see how it translates, right? So when people are talking about algorithms and they're independent of a machine, when they start talking about we see that when I'll tell you about that a little later on, about log time versus linear time. They're talking about orders of magnitude of difference in the performance of this thing, right? Many, many orders of magnitude, right? So let's talk about runtime already. So if somebody made this statement, right? He said, look, binary search, I noticed I had 100 elements, I ran binary search, it ran about 7 nodes. Whereas simple search take 100 nodes. So I come to the conclusion, look, binary search is 15 times faster. Okay, and now I'm going to use it for 1 billion elements, and I'll still be able to use simple search, right? Because if I do the same kind of math, well, look, 15 times, well, this will be 450 milliseconds for simple search, right? Obviously, just some examples before you can tell us a very flawed way of looking at it. It doesn't scale the same, right? In the first place, so the first problem is that algorithms are not code. So we can't talk in terms of an absolute time. We can't say milliseconds because we're not talking about code anymore, and we're not talking about a specific machine. Because I could take the same code implemented on two different machines with two different processors and two different sets of memory, and it'll run differently in two different machines, not standardized across machines. Because a better processor might make it run faster, more memory, the computer system itself will help you out. I can't talk in terms of absolutes. The second problem is that algorithms in general, growth is very important, right? When people start to study algorithms and they started trying to talk independent of the machine that we were running on, they said, well, one of the problems we're encountering is that people want to run these algorithms on more data, more and more data, more data. Right? We've come to 2024 now, and we have so many uber tons of data, it's hard to deal with. Yeah. So they wanted to be able to talk and wanted to be able to analyze algorithms in terms of groups, not just in terms of runtime. Runtime is important, but groups. Cool. So if we want to know, at least that is part of our goal, to figure out how long will it take an algorithm to run as the amount of data increases, right? And that's where this thing called big O comes in. Okay. So if you have a list of size n, simple search will need to check each element in. Therefore, it will take n operations. Cool. Thus, the runtime in big O notation, or the order of the algorithm, or means order, is O to the n, also known as linear time. Cool. So I could describe an algorithm and say it's an O to the n algorithm. Right here. Again, notice it doesn't tell you anything about the speed in seconds. What it does is allow you to compare the number of operations. And it tells you something about how the algorithm will grow with growing data, right? You have n items, it will grow linearly with n, right? Underline line, because I know it's going to sound a little strange for me to say now. By the end, hopefully you understand what I mean by this line, but it's going to be what big O is. It is called an asymptotic tight upper bound on groups. Ignore the weird phrasing, you'll understand, right? Ignore the asymptotic tight part. I'm going to say the word upper bound. It means that growth will never be worse than this. Growth will never be worse, right? Not the runtime. Anyways, similarly, binary search needs log n operations. So therefore, in big O, it will be log n, right? And again, because we talk about computers, more often when we say log, we talk about log base 2, right? Unless somebody says otherwise, we're talking log base 2. So they leave off the 2, they talk log base 2, right? Not base 10. All right, so consider this algorithm. If I had to create a grid, and I was creating it, method 1, I draw each square in the grid one after the next after the next. Method 2, we fold in the paper. After 4 folds, look, I have the grid drawn. Was the complexity of the first one versus the complexity of the second in big O? So I draw one box for each one of the numbers, all 16 numbers. Or I just fold the paper one over one. So for the first method, I just draw each box, and I have 16 boxes to draw. What is the complexity of an algorithm like that? I'm going to assume you're looking at me blankly because it's finding a question too simple. Or is any question generally thought? Actually, I don't know. We don't understand the question. I don't know. It's either if I had too simple and they think there's a trick, or you don't understand the question. So if you don't understand the question, please tell me. Well, OM, yes, correct. Because if you had 20 boxes, then you have to draw 20 boxes, right? The more boxes you have to draw, more. So therefore, the first method is linear, or OM. right? Or the second method, or we just kind of divide people, keep folding. Divide it once, you get 2 boxes. Divide the next time, you get 4 boxes. Divide again, you get 8 boxes. Divide one more time, 16. Right? We keep folding people. So what is the complexity of the second one? Yeah, log n, right? Because I can do it in four moves. Log of 16. So yeah. All right. I want you to recognize that specifically because, well, the first reason is somebody might tell you algorithm like that. I want you to get into the habit of listening to the person says and trying to come up with an idea of how long will this thing take. Okay. All right. Let's think about the relative growth of that algorithm, of this problem. Sorry. Imagine you had an algorithm that fits each one of these different magnitude orders of growth, right? Going from left to right, it is more flashy versus more just slugged from Monsters Universe. Yeah. The time ground, the growth in time gets worse as you get more to the right as opposed to more to the left. More to the left is pretty good, more to the right is like, you don't want to encounter that. So if you can assume you can do one operation in 0.1 seconds, and you have 16 boxes with 256 boxes with 1024 boxes. If you had an algorithm one was log time, that's the first one. Then by the time you get 1,000 boxes, you can do it in a second. Right? So the first one is what we call log time. We talked about the next one, which is linear time. Yeah. He's getting out of the rules. The next one is n log m, which is what you call linearistic time. Yeah, the combined log and linear to get logarithmic and linear is, I don't know, whatever, right? Okay, cool. The next one is quadratic time, where n squared, you know, the word quadratic. Obviously, n squared, you have other ones alongside, you have the polynomials, quadratic, cubic, quartic, quintic, the polynomials. And then all the way on the right, you have factorial time. Come across a factorial time, and you're like, right? To draw 1024 boxes will take you, we'll all be dead. The world would have ended. Yeah. You don't want factorial time. Whenever you have a factorial time problem, computer science is like, okay, we need to do something, right? And we'll talk about what something is for this course. Cool. This is a diagram that's showing you how it grows the time alongside one another. So most common complexity class, right? All the very bottom, the one that you want in life, O to the 1. O to the 1 means constant time. Doesn't matter what you do to n, doesn't matter how many things there are, it will always give you the answer in the same amount of time, regardless. That's O to the 1. Some people write O to the k, right? Constant time. Next level up, next best is logarithmic time. Really great algorithm, right? Logarithmic time, we have binary search as a good example, right? And you have linear, which is your basic simple search type algorithms. Linearistic, a good sorting algorithm would be like that. Your popular ones like quick sort, etc., are in that kind of brackets. Right? Those are kind of bad, but not too horrific. Yeah. Then you get to the truly horrific guys. Any polynomial time, which are most sorting algorithms out there. This is why we'll spend some time talking about it, because it gives us a way to look at some bad algorithms. Exponential time. Truly terrible. I think Tuesday I'll give you an example of one of those. And factorial time. Hopefully we don't encounter any of them. Cool. So that's an idea of what kind of brackets I want you to be able to put algorithms into when we are talking about runtime. Okay. So here are some examples, and I want you, for these really hard examples, to tell me the complexity. Okay, take a breather. Yeah, setting you up. You guys okay online? Nothing extra online, all right? All right. So let's go with the first hard algorithm. Oh, look at the next one. You're okay. Okay. Good. All right. So I decided to use my friend here. Right? Midas. We have a Death Star. And we would like to visit some planets for reasons. Okay? Good. Good. Good idea. Unfortunately, that stuff fuel is expensive. And what is one to do if you want to just earn a dot's salary? It appears. Anyway, so the problem with this fuel idea is that perhaps you might be passing in some black holes on the way to some of these worlds. There's lots of energy to do that, right? So we need to plot our route very, very carefully. So if you're working for me, you want to make sure you get the route right. So let's consider, if you had to visit two planets, how many different ways you could visit those two planets? I have to go to Aldebaran and Naboo. How many different orders can we visit them in? Two. First, we could go to Aldebaran and then we could go to Naboo. Or we could go to Naboo first and then go to Aldebaran second. Okay, cool. Two routes. I can figure that out. That A or B. Right, good. What about three planets? Not waiting. Three planets. Because why you don't want to sit lower as your master? You want to quicker than us. I'm going to force choke you now. Mm. I heard six. Yeah, we can hold all around safe, and then we have two possibilities. Or we can hold Naboo in the first, and then we have two possibilities for Naboo. We can hold Jeddah first, and we have two possibilities. So that's 3 times 2. Okay, 6. All right. So what about 4 worlds? Well, we know 3 worlds will take us 6, right? So if we hold all around first, then that's 6 times. If we hold Naboo first, it's another 6 times. So it's now 4 times 3 times 2. So that's 24, right? Okay, cool. I can't do math. Yes, I think Das is like, what if you had to do 16? Yes, 16 factorial. So in the end, will be n factorial. Very bad idea. That's not happy. Anyways, for traveling data problem, this is what factorial looks like in the end, right? We recognize this is a simple factorial problem, right? So notice what happens when we just get a modest number of worlds to do. We just have to get 30, we have to compute. I'm not even going to try to read that number, that many possibilities. Okay? In reality, it'll take you several millennia to calculate that if you have to brute force search through the space of all those kind of ways, right? So that is one of the factorial problems that we hope to never send you. Okay? Unfortunately. All right. Okay. Let's try a bit more of a less fun example. I'm going to multiply two numbers in 2 different ways. You tell me how long you think it'll take. Right? Method 1. You ever heard of repeated addition? Okay. So let's just multiply, say 2 by 3, that's equivalent of adding 2 3 times. Yeah. So it is R2, and R2, and R2 becomes something. That will be 2 times 10, and R2 plus 2 plus 2 plus 2, 10 times. So how long do you think, in general, algorithm like that will take? What kind of order you would expect over this? Repeated addition that moves each time the number changes. If you have 10, you have to multiply, you'd have to add 2 how many times? You have 20, how many times you have to add 2? So you have Z, yeah? Okay, cool. Now, I don't know how it is in primary school these days. My parents used to beat the crap out of us if you didn't learn your multiplication tables. So then if somebody said 2 times 2, I'd be like, 4. Okay, I know that for both numbers. So if you wrote down the numbers somewhere and stored it somewhere like a array, and we just looked up each time the answer you wanted, what kind of order do you think we talk about there? Okay, if it's 2 times 10, I go in array and I look up the one that says 10. All right. If it's 20, I'll go in array and look up the one that says 20. If it's 60, I'll go in array and look up that. Does my action change? It does not change with no matter which number it is. It's just go to the array, what's there? Cool. So what order do you think that is? 1. Constant time, right? Much faster. That's an example of a constant time algorithm. So if you store stuff in arrays, because we could just go and look it up, it's the same action we do every time. The same, I'll go and look it up. Yeah, I'll go look it up. Cool. Anything you see where you're storing stuff in arrays and stuff, more often than not, we're talking about something that might be constant. Right? There's a trade-off there. Obviously, you have to expend some memory to pull that off, right? But you get great runtime. All right. What about this hard little example here? Sort my playlist. So here's a playlist of some songs here now, right? And I have a play count for each one of these songs. Here's one way I could sort this list in order of play count. Right? I want to figure out which songs I listen to the most. Right? First, I can go through my list and find the song I play the most. Right? In this case, apparently it's Radiohead. I take that one and I put it into a second list. So I looked through all, found one, and went to that other list. Okay, and I remove it from the list. And I go and look at my list again, second time. Which one is played the most now? Then it's apparently Kicho Kamal. 2 seconds. 141 times, he went second time. Okay, move that from the list now. And then I looked up again to the end of the list again. Okay, what's going to be most? Put it in the next. Over and over and over until I come up with my sorted list. Right. So, what kind of order do you think we talk about here? Not so hard, right? I don't know when you want to hint. Anyway, online, I think a lot of people get easily. I think they know this one offhand. But you're supposed to know this offhand. Have one bigger. All right. So people who have trouble getting to the answer, that's considered piece by piece. So if we're just talking about the part where I have to just find the thing that is played the most, then you want that. Because I'm doing that over and over, right? If I have to just find anything that's played the most, how would I do that? I have to go through each item in your list and just be comparing to see if I've got the max or not, right? So how long does that take? Just finding the max. Hello. It'll take you n. That's a longer list, the more things I have to look through. I have to go from beginning to the end. Right? It take me n steps, regardless, to find the max. Cool. So I have to do that for the first time. Yeah, and then I have to do it again. Second time. Third time. So if there are n items in your list, I have to do that, find the max n times. So I have to do a thing that costs me n steps n times. N times n. So this is an example of an n squared algorithm. That's how they get the n squared. You first do the thing that you're doing repeatedly to figure out how much steps you'll take to do that thing. And then figure out how many times you want to do that. Yeah? Make sense? Yeah. Like I said, there's a way to start to think about these kind of problems. But We'll do a lot more examples later on, right? So again, this is what I want you to be able to do, right? Start learning to reason it. Oh, come on, Augustine. Okay. All right. This one I'll leave you to work at home. I don't want to spend too much time behind these examples. All right. Try to figure out how much time you think it would cost you to multiply two n by n matrices together, right? If you want to just Google the answer is NQ, the naive. There are other methods, but the naive way that you would learn in high school is IMQ, right? Part of the whole polynomials, those guys, right? So what I'd like you to do, if you this way, this is just for your own practice, way to get accustomed. This one's a little more difficult, but try to convince yourself why matrix multiplication is cubic growth, right? If you sit down and do a matrix multiply by hand, you're real. Think. Else, if you're stuck and you can't do it, I'm sure Google has the answer, right? I'm pretty sure. It's a pretty famous one. All right. So that gets us to other algorithmic measures other than the big O we've been talking about. So big O is what I say, asymptotic tights upper bound time, right? That's what I said. So here's a summary on big O. It is an upper bound on time. Does that mean it's the worst case? This is a hard question. The worst case time. And because I know how the way Anil and Akash talk, you might get confused. Some people say that this is worst case. But is it actually worst case? If you say this is upper boundary time, does that mean it's the worst case we're talking about or no? I know it's hard to conceptualize. All right, cool. Uh, Big O is about growth, right? Everybody's convinced of that. Big O is about growth. That's what we talk about here. We talk about growth. So why I can do that? Anyway, right. So let's use the simple switch as an example. If I had 10 things to switch through, it'd be 10 steps, right? 20 things would be 20 steps. 50 things would be 30 steps. That's how it's growing, right? So if I'm saying it's worst case linear, that means I talk about growth is a linear growth. Okay. But there's also for simple search, I talked about worst case and average time, right? In worst case, it's n, on average, it's n on 2. So let's consider those two in big O terms. The worst case growth, if I had 100 items, it would take 100. 200 items, it would take me 200. 300 items, it would take me 300. Or the average case. Out of 100 items, what was the average case? If say, if I had 200 items, what is the average case? 100. 300 items, what's the average case? 150. So doesn't the average case grow linearly as well? Grows. So you can have big O for the worst case times, which we could say is order n, and we could say we have big O for the average case time, which is order n. Cool, right? But what we are saying about, what Big O is saying about both the worst case and the average case is that they will both go linearly. And therefore, it will not grow when the next one goes up. It will not grow n squared. Yeah, it will never grow. It will grow by some constant times n. But the constant is how long it takes you to do the whatever it is you do. Yeah. It does not say that one linear algorithm will take longer than another. All it says is it will grow at its level. So that upper bound, some people use the word worst case instead of upper bound. And Anil and Akash informally might say that. Okay? Because it's the upper bound, and therefore we talk about the worst case growth of the thing. Then the worst case growth linear. But we might be talking about the upper bound of the worst case times, or we might be talking about the upper bound of the average case times. But see, to see the word worst can happen twice in the sentence. So sometimes, especially if you are doing it next semester with Ashton and Anil, be careful how they use the wording. I will try my best not to do it because sometimes people do that informally, and you have to decipher which worst case we're talking about. Yeah. So I'll use upper bound when I talk about O, and I'll use worst case or average depending on which case I talk about. Okay. But just be clear. Okay. So why would we want to know about the worst case times or the upper bound of times growth of algorithms? Because it's generally reassuring. We know it's not going to grow worse than that. Okay, as we get more and more data. That's why people talk about it. Other part of the definition of O has to do with asymptotic tightness. Right. Don't worry too much about this for this course. I don't really go into it into detail. From a mathematical point of view, it means that so you know what linear looks like on a graph, right? It's like a straight line. Right? If I draw a straight line. What if the gradient was more, multiply everything by constant, right? It means that I could have two linear algorithms that are growing at two different rates in reality. But I do not differentiate, Big O does not differentiate between those two linear algorithms. Yeah, that's what it means by asymptotic tightness, right? A constant times n, we don't care. So if somebody wrote something was Big O of 10n, we could simplify that and say Big O of n. We don't care what constant for n because it's all n. Okay, that's what Big O means. Little o is another one you could have that does talk about asymptotic tightness. Yeah, so I would not describe what do you call this thing? Simple search as little o n. I would describe it as little o n squared, next level up. But I'm saying it's not going to grow anywhere as close as the n squared algorithm. Right? No matter what constant factor it has. So we don't do little o in this course, so don't worry too much about it. But for Big O, ignore constant, right? All right. Other than big and little o, there's also big or omega. So just like you have an upper bound, you can have a lower bound growth. And similar to how people talk about worst case, they talk about best case, lower bound. So again, it's a lower bound, it's not going to be better than that. Gross, it's not going to be better, right? So should you care about the lower bound growth? Yeah, in reality, yeah, more often not. So if you go and talk to the comp sci guys, they'll all be like, why are we even discussing it, right? Now, this happens a lot when you have systems when determinism is a strong constraint. Determinism. So you talk about that in what you call mission critical systems. The kind of thing where we pay lots of money for it to not shut down. The plant, we want to make sure it doesn't shut down. We want to make sure the pacemaker keeps running. We want to be sure it happens between these two bounds. It will never go outside these two bounds. We are worst case this and best case that, right? Cool. Be sure. Because it helps you with much larger things, right? You would see people who are dealing in mission critical systems talk about this. The comsci guys don't care because they do consider systems, and why should they care? If it's best case, great. We got the best case. If it's not, we don't care. The vast majority of computer science people don't talk about it, right? And of course, there is big theta, where you talk about we can capture both upper and lower, right? Big theta. And again, people mix this up with outer space, but what big theta means is that we have both the upper and a lower bound. So it's very, very deterministic. Okay? And the upper and lower are the same thing, right? You would say big theta when upper and lower are the same order. Right? Else you'd record O separately and omega separately. But with O and omega are the same thing, if they both end, you will say other shortcut theta of n. Yeah. Anyways, I'm gonna go into that. All right, cool. So what time are we at now? I suspect it's about midday anyways. Okay, I'm really looking at. So let's just talk about where to go from here. If we choose to keep doing this, can it? So so on Thursday, if you choose to come Thursday, we're going to be doing our equation type work. We'll look at the equation ratio. I don't like how Augustine teach it. Look at that because I don't think they talk about call stacks in here on much, but I talk about it in that video. So don't come here without understanding what a call stack is. Cool? I talk about it there. And I would like the year twos to come and talk about this answer. Everybody do it obviously, but year twos, meaning you two online, be prepared to talk about this implementation I'm asking you to do. I want you to use recursion and the loop, the two different functions I want you to write, to add up all the elements in an STL vector, right? So try it on your own first. Obviously, you're going to be able to find this code online. It's very basic. Yeah. And then between the two of you, and if there are any other year twos to show up, we're going to have sacrificial lamb to, well, explain how the thing works. Sorry, explain how it works in the context of a call stack. Cool. And I'm just doing that specifically so I know that we all talk about the same thing when we talk about call stacks. And then we'll go off and I'll show you why understanding call stacks is important. Right? So that is the main thing I will be terrorizing year twos with. So I need something to terrorize year ones on. And I would like you to review data representation before the next class. Marcus told me you all did it in 1014. I had a conversation with him the other day. Thankfully, he happened to mention this in passing. But be able to talk about the basic data representation thing, right? And of course, amongst you here, choose your sacrifice. You want to choose sacrifice now? But they'll know not to come. Okay. It has been volunteered. All right, cool. And if you can, for next week Friday's lab, again, this Friday, I'll just do an online Zoom thing. Do those things, right? You could even walk with the code to the lab as well. I wouldn't think. So I save you some energy. Right, and that just leaves us with where we go into next time, which is, there we go. What you'll be discussing with it. We'll be talking about memory in general, right? Memory related issues. Cool. So I think that's it for me, more or less. If there are any questions before you guys